All right. Thank you for the opportunity to speak. So today I want to tell you about a project with Hirofumi Sasahira and Matt Stoffergen. So this is about lattice homology and Seiberg-Witten-Floer spectra. Firstly, what is this talk about? So this is about the main object of study is going to be the Seiberg-Witten-Floer homotopy type. So this is an invariant for three manifolds, or I guess more specifically rational homology spheres defined by Ciprian. I don't really think that I have to talk that much about what Seiberg-Witten-Floer homotopy type is to the current audience, but let me briefly do so anyway. Given let's say rational homology sphere with a spin C structure, what this is associated to the pair y comma s. The Seiberg-Witten-Floer homotopy type is a space, specifically a finite CW complex, or more precisely, such a space defined up to suspension. So it's a homotopy type. The equivariant, the homotopy type of this space, or rather the equivariant homotopy type of this space, as I'll talk about in just a moment, is an invariant of our pair y comma s. Okay. And the homology of this space, or again, the equivariant homology of this space, is what's called Seiberg-Witten-Floer homology. And Seiberg-Witten-Floer homology is now known to be isomorphic to monopole Floer homology or Heegaard-Floer homology, or whatever other nice Floer homology theory that probably everybody is familiar with. So what do I want to talk about in terms of the Seiberg-Witten-Floer homotopy type? The Seiberg-Witten-Floer homotopy type, or sometimes I'll say the Seiberg-Witten-Floer spectrum, is currently only known for an extremely restricted class of manifolds. So of course, there are sort of, as you can imagine, rather trivial examples such as S3 lens spaces, more generally free manifolds with extremely restricted geometry like elliptic manifolds. But actually on top of that, there are basically not many calculations. Essentially, the only non-trivial calculations that I'm aware of that appear in the literature are Brie-Scorn homology spheres of the form sigma 2, 3K. And I'll talk about why it is that these things are understood in just a moment. But to the best of my knowledge, this is an essentially exhaustive list of all three manifolds for which the Seiberg-Witten-Floer spectrum is understood. Of course, you have structural results about orientation reversal and perhaps connected sums, but in general, the Seiberg-Witten-Floer spectrum is a thing that's very, very hard to calculate. And let me point out that the Seiberg-Witten-Floer homology is, of course, widely calculated. One reason being that it's isomorphic to Heegaard-Floer or monopole Floer homology, or things, more computable theories. But the homotopy type is not widely computed, and of course that's because for these other homology theories, there are many computational techniques that are known. You often have versions of these for knots, and you have some sort of Sergi formula, or you have some other structural tools that allow you to calculate the homology. Even the most basic of these is only starting to be developed for Seiberg-Witten-Floer homotopy. In any case, the Seiberg-Witten-Floer spectrum is really computationally, I think, mysterious. And so what this talk is about calculating the Seiberg-Witten-Floer homotopy type in some non-trivial cases for some reasonably large class of three manifolds. So that's what I want to tell you about. Okay, so what three manifolds am I going to attempt to compute the Seiberg-Witten-Floer homotopy type for? So this will be a particular subclass of what are called plumb three manifolds. So I think probably most people are familiar, but so if you take a plumbing of two spheres, so Y will be the boundary of a plumbing of two spheres. So if I have a plumbing of two spheres, then the combinatorics of the plumbing are included in what's called a plumbing graph, which I will denote by gamma. And given a Plumbing graph gamma, it turns out, and I'll talk, this will sort of actually be a significant part of the introduction of the talk. We define a sort of combinatorially constructed CW complex. And what I mean by combinatorial is there's no analysis, there's no pseudo-holomorphic anything. You really just look at this graph and you write down a CW complex, okay? And the construction of the CW complex is inspired by this object called lattice homology, which I'll talk about in just a moment. And this, the thing that you write down, it's not just a finite CW complex. It also admits a S1 action, okay? And we prove that the homotopy type of this combinatorially constructed thing actually computes the Seiberg-Witten-Floer homotopy type of the boundary of the Plumbing, okay? This will hold for what are called almost rational plumbings. So there's some subfamily of plumbed rational homology spheres called almost rational plumbed homology spheres, for which this correspondence holds. I'm not actually going to carefully define for you what this subfamily is, this class of almost rational plumbed manifolds. I'll say what the relevance, what property matters in just a moment. If you don't know what these are, you can just think of these as cipher-fibered rational homology spheres. So every cipher-fibered rational homology sphere, maybe with base orbifold S2, is such a three-manifold. So we calculate, one particular corollary is we calculate the Seiberg-Witten-Floer spectrum for all such three manifolds. Again, let me emphasize before, it was only sort of known for Brieskorn spheres of the form 2, 3K. So this is really an expansion of the three manifolds for which the Seiberg-Witten-Floer spectrum is known. Okay, so my goal will sort of be to explain to you what the construction is, how we construct this what we call the lattice homotopy type, where it comes from, and how in the world are we going to prove that this actually calculates the Seiberg-Witten-Floer spectrum of these three manifolds. Okay. All right. So, but before I do that, let me give a very brief attempt at a motivational speech for Floer homotopy. I don't think that, again, I really have to convince this particular audience of the merits of Floer homotopy, but let me do so anyway. Just a brief reminder of the some of the initial usages of Floer homotopy. So I think it stems out of the four-manifold side. I think that maybe the first very high-profile usage of ideas in Floer homotopy was the proof of Furuda's theorem, the Tenyé's theorem, which currently has no proof using Floer homological methods. If one wants to sort of go a little bit more into three manifolds, even though I think it's sort of more like 3.5 dimensions, Floer homology is generally not as good as answering questions about indefinite manifolds and indefinite bounding. So if I give you, let's say, an integer homology sphere, and I ask, what sorts of four manifolds does it bound? It's sort of a standard thing that Floer homology is very good at providing obstructions to things like saying, my three manifold Y does not bound any negative definite manifold or positive definite manifold, and so on. Floer homology is generally much harder to leverage questions about, if I asked, does my three manifold bound certain indefinite intersection forms? Floer homology, although not impossible, is often much harder to use to answer such questions. Whereas Floer homotopy generally is much more flexible at answering such kinds of questions. So let me just give a sample theorem due to Ciprian. The exact statement of this theorem is not important. I just give it as an example. So here you can see in the statement of the theorem that if I have a homology sphere Y, then turns out that you can, using the Seiberg-Witten-Floer homotopy type of Y, you can define a numerical invariant, which is called kappa of Y. And kappa of Y puts some constraint on the possible spin intersection forms that Y can bound. Okay, this theorem is not really important for this talk. I just give it as an application of the kinds of things that you could do in 3 or 3.5 dimensions with Floer homotopy. Okay, and of course, the original Manelovsky's original disproof of the triangulation conjecture, was derived from his development of pin-2 equivariant Floer homotopy, although really the numerical invariants that he used were defined on the level of pin-2 equivariant Seiberg-Witten-Floer homology. Okay, so these are some topological reasons why you sort of might study Floer homotopy. I think in reality, if one asked somebody who did Floer homotopy, the honest answer would be you try to do it because you can, or it's there. The idea of doing Floer homotopy is part of a very broad program, which involves all these different homological Floer homological invariants, Seiberg, monopole Floer homology, even other invariants like Kovanov homology or not Floer homology. And the goal in each case is to find a space version or a spectrum version of each of these homology theories. So you want to, instead of associating to your object a homology, you want to associate to your object a space whose either homology, regular homology of that space, or equivariant homology of that space recovers your favorite homology, homological invariant about that space. And this is a very old program dating back to Floer and Cohen, Jones, and Siegel, and it has attracted a lot of interest in all of these different settings. So the Seiberg-Witten-Floer homotopy type, I think, in some sense, the first successful instance of doing so. So let me pour cold water on my own theorem for just a moment. So the most basic question you could ask, having developed a Floer homotopy type for, in some setting, is that, well, is it stronger than the Floer homology? So what is a case in which I have 2-3 manifolds which have the same, let's say, monopole Floer homology, but have different Seiberg-Witten-Floer homotopy type? And there are no current examples, at least in rational homology spheres, I think. I think actually amongst any example, but there are no current examples which are known. And so you could say, well, Irving, you just told us that the homotopy type is not computed for many 3 manifolds. So surely now you can give us an answer. And unfortunately, the answer is still, I don't know. Actually, our theorem is, as I will try to explain, actually, essentially shows that in these cases, the Floer homotopy type doesn't contain any more interesting information than the Floer homology. So it's still, I still don't know. I should note that in these other cases, and for example, the Kovanov homotopy type, I believe there are certainly knots which are distinguished by their Kovanov homotopy type, but not their Kovanov homology. Unfortunately, we essentially show that for these 3 manifolds, the Floer homotopy type can algorithmically be determined from the Floer homology. So, we can't provide any sort of example of this question, but nevertheless, I will, it is not obvious for these 3 manifolds that the Floer homotopy type should contain no more information than the Floer homology. So in some sense, the Floer homotopy type is not interesting, but it's a theorem that it's not interesting. Okay, so that's what I want to sort of talk about. All right, so that's as far as the overview goes. So now let me talk a little bit more about the details of Seiberg-Witten-Floer homotopy. Again, I don't think I have to go into so much technical detail for the present audience, but let me sort of say a little bit more about why Floer homotopy is hard. So again, what's the basic idea? Well, in Seiberg-Witten-Floer homotopy or Seiberg-Witten-Floer homology, one has One is essentially studying this thing called the Chern-Simons-Dirac functional, CS. Maybe I should have written CSD. This is a functional on some, infinite, I mean, there's some space of connections, cross spinors, and I mod out by this gauge group, but I don't particularly think I need to go into the details. So one studies this functional, the Chern-Simons-Dirac functional. And in, let's say, monopole Floer homology, one studies the critical points of this functional, and you look at zero-dimensional flow spaces between critical points, or rather one-dimensional flow spaces modulo the action of R. And when you look at this zero-dimensional flow spaces and critical points, and you do essentially the analog of infinite dimensional Morse theory, one gets a chain complex, which of course is the monopole Floer chain complex. And this gives you the monopole Floer homology. Very roughly speaking, to obtain Seiberg-Witten-Floer homotopy, one has to look at all flow spaces between critical points of the Chern-Simons-Dirac functional. So these are higher dimensional moduli spaces of flows. And the point is that if you do some sort of finite dimensional, I'm glossing over a lot of detail, but all of these higher dimensional spaces of flows fit together to give some CW complex. And the homotopy type of this CW complex is the invariant, the Seiberg-Witten-Floer homotopy type. Okay. So let me give you an example. Okay. So I will probably, these are the three manifolds which I mentioned previously. So here's sigma 237. So the Seiberg-Witten-Floer homotopy type of sigma 237. So throughout the talk, I'll be a little bit cavalier with the distinction between a space and a spectrum. But so here I have the Seiberg-Witten-Floer homotopy type of sigma 237. This is basically you take two S2s and you glue them together along the north and the south pole. Okay, and that's the Seiberg-Witten-Floer, the space associated to sigma 237. And as I'll talk about in just a moment, actually the Seiberg-Witten-Floer spectrum is not just a space, it's an equivariant space. It comes with, well, first I'll talk about it as an S1 space. So it comes with an action of S1. In this particular case, the X1 action is sort of just given by equatorial rotation of each of the two spheres. Okay, so this is SWF of sigma 237 on the top. And SWF of, more generally, sigma 23K is very similar. It's displayed along the bottom, and it's basically just you have more two spheres. And the action of S1 is equatorial rotation in each one. Okay, so these are the examples which are known. And maybe I'll say a little bit about what enables these examples to be known. Okay, so how does one actually, one can, it's a fair question to ask. Is it possible to understand something like the Chern-Simons-Dirac functional directly, from, sort of from the ground up without using, some surgery formula or anything like that? Can one actually compute, the critical points and, the differential of the chain complex directly from the definitions? Well, actually, it turns out that in some examples, the answer is yes. So in particular, there's this paper by Morovka, Ozvath, and Yu, which let's say for cipher fibered spaces, integer homology spheres, cipher fiber spaces, there is actually essentially a direct computation of let's say the monopole Floer homology. And the computation goes by explicitly identifying the critical points of the Chern-Simons-Dirac functional. So that's possible to do, to identify the critical points of your functional explicitly, enumerate them explicitly. And then, but to my knowledge, there are very few, if any, computations in the literature in which something like the moduli spaces of flows between critical points is explicitly understood. So in the case of monopole Floer homology of cipher fiber spaces, what happens is that you can identify the critical points of the Chern-Simons-Dirac functional, and you discover that all of the critical points, or at least the irreducible critical points, lie in the same mod2 grading. And therefore, you observe that the differential is necessarily 0, and you wash your hands and you're done, and you pretend you've sort of totally solved the question. This phenomena occurs, also in other Floer theories, like instanton Floer homology for Seifer fibered spaces. And so, of course, in that way, it's possible to compute the chain complex directly. But of course, you can't compute the homotopy type. That doesn't help you for computing the homotopy type, because just because the critical points lie in the same mod2 grading, you could, of course, have some non-trivial space, some non-trivial moduli space of flows between two critical points in very different grading. So that does not, that could still result in a very interesting homotopy type, even though the differential on the chain complex is, of course, trivial. So, that's why a direct computation, that's an example of why direct computation of the Seiberg-Witten-Floer spectrum is very, very difficult. Okay. Now, there is, of course, a case in which the computation of the Seiberg-Witten-Floer spectrum is still sort of once again trivialized, and that occurs when all of the critical points of the Chern-Simons Dirac functional lie not just in the same mod2 grading, but in fact lie in the same grading. Because then, of course, again, you can't, then you certainly can't have non-trivial moduli spaces of flows between those critical points. And that's actually what occurs for these examples, okay? So the only, to my knowledge, the only examples essentially in which, broad class of examples in which the Seiberg-Witten-Floer homotopy type is computed are examples like S3 and lens spaces and elliptic manifolds, for which essentially understanding the critical points of the Chern-Simons Dirac functional is trivial. There are no irreducible critical points. Or examples in which the irreducible critical points all lie in the same grading. Okay, in which case, it essentially understanding moduli spaces of flows between the critical points is trivial. That's not 100% true, because for experts, that that you have to take into account the moduli space of flows that go into sort of the reducible and the moduli space of flows that go off to infinity. But the fact that there are no flows between critical points, your irreducible critical points, as you might imagine, vastly simplifies the possibilities for the Seiberg-Witten-Floer homotopy type. Okay, so that's what happens in the known examples. Okay, and obviously that's sort of, that's sort of not a psychologically, feels not very psychologically robust situation to be in. Okay, so we want to expand our family of computations. Okay, so again, so I've sort of punted it off. So let me just make sure that we're sort of, I really sort of say. So the Seiberg-Witten-Floer spectrum comes with, is not just a space, it comes with, in this context, I'll mostly talk about an S1 action. The reduced, the S1 equivariant homology of this space is what's called the Seiberg-Witten-Floer homology. Okay. And more specifically, let me just remind you what I mean by this. So you can take what's called the S1 Borel equivariant homology. You take your space X, you cross it with EG, where G is S1 in this context, this infinite, this contractible space on which S1 acts freely. You cross it with EG, you mod out by G. This is often called the homotopy quotient. And you take the regular homology of this space. This is the S1 Borel equivariant homology. And I will ask you to remember this, this correspondence. So the S1 Borel equivariant homology of the Seiberg-Witten-Floer spectrum is the analog of the plus flavor of Heegaard-Floer homology, HF plus. Okay. There are some slight variants of this construction, which will actually be more relevant for the talk at hand. You can take what's called the co-Borel homology, the S1 co-Borel homology. This is the analog of HF minus. You can take what's called the S1 Tate homology. This is the analog of HF infinity. I'm not going to define exactly what these are, but the point is there are several slightly different flavors of S1 equivariant homology that you can take, and these correspond to the slightly different flavors of Seiberg-Floer homology. Okay, but the different flavors will be relevant in just a moment. So, all right. And the other most basic example that I'll ask you to remember is the Seiberg-Witten-Floer spectrum of S3 is the simplest thing it can be, which is S0, 2 points, sort of with the trivial S1 action. Okay. All right. So that's the introduction to Seiberg-Witten-Floer homotopy that I wanted to give. And so now I want to talk about this lattice homotopy object, this thing that we construct, which we claim computes the Seiberg-Witten-Floer homotopy type. And I want to describe where the construction comes from. And in order to describe where the construction comes from, I have to tell you about this, this previously existing invariant called lattice homology. And the lattice homotopy type we construct will somehow be an upgrade of lattice homology. Okay. All right, so what is lattice homology? So lattice homology is a combinatorial invariant for 3 manifolds introduced by Osvath and Szabo. Okay. Let me first talk to you about sort of the overall output of lattice homology. Okay. So if I give you a plumbed 3 manifold, which is presented as the boundary of, let us say, a negative definite plumbing. Okay. The output of this thing I call lattice homology is what's called a graded root. Okay, I'm not going to give the precise definition, but a graded root is just something that's like in this picture. It's some sort of infinite tree. Okay, the tree is sort of an upwards opening tree. It has an infinite downward stem. Okay, and this tree defines an f-adjoint U module just by saying each vertex of the tree corresponds to a generator over f being the field of 2 elements here. And the multiplication by U is given by following the edges of the tree downwards. Okay. So in this example that I have here, this represents this graded root represents a f-adjoint U module, which has 2 generators in the uppermost grading. So the gradings of the generators will correspond to the heights of the vertices in the tree. So this graded root has 2 generators in the uppermost grading. And if I multiply them by U, then they become the same generator in grading 2 lower than the highest grading. And then I can continue multiplying by U, and this will give me sort of infinite tail of generators going down to negative infinity. Okay. So somehow the point is, if I give you a y, which is the boundary of negative definite plumbing, then out of the combinatorics of the plumbing, there's some mysterious way for writing down this infinite tree. And if I take the tree and extract from it an f-adjoint U module in the manner that I just described to you, it turns out that the f-adjoint U module I extract is known to be isomorphic to Seiberg-Floer homology, at least for certain kinds of plumbings. Okay, and this is what's called, this tree or this f-adjoint U module equivalently is what's called the lattice homology of Y. Okay, so the lattice homology is isomorphic to Seiberg-Floer homology. This is an amazing theorem because a priori Seiberg-Floer theory requires a computation. Inside the computation, there are all these counts of pseudo-holomorphic curves, but I claim to you that this tree is totally combinatorially constructed from just looking at the plumbing graph, the combinatorics of this plumbing. Okay.
So Irving?
Yes.
So is that so do I understand correctly that you could, if you knew the Seiberg-Floer homology, then you could just sort of write it down as a tree in this fashion? Does it go both ways, or is it that you're
a priori, the tree actually contains slightly more information than the Seiberg-Floer homology, because in some sense, the tree is giving you a preferred basis for the Seiberg-Floer homology, but it turns out that in practice, in most situations, the distinction is not very important. It's a good question.
And is it supposed to be that each dot is a copy of F then?
Each dot is a copy of F. It's a generator.
So I see. So if you take the popular F2, then somehow that's the same.
Oh, well, sorry. For me, F will always be F2. So
yeah. So
okay. All right. So where does the graded root come from? Okay, so let me try to explain lattice homology. So this will take a little bit, but actually once I explain it, then in fact, it turns out that our theorem about Seiberg-Witten-Floer homotopy is going to actually fall right out. So where does the graded root come from? Okay, so let me give you the idea behind the construction of lattice homology. Okay. So here I have this three-manifold Y, which is gotten as the boundary of this negative definite Fleming W. Okay, and as we all know, Floer homology, Heegaard-Floer homology, satisfies. I talk about Heegaard-Floer homology here just because it's the original setting of this lattice homology object. In just a moment, I'll explain what this has to do with Seiberg-Witten-Floer homology and Seiberg-Witten-Floer homotopy. But as we all know, Heegaard-Floer homology satisfies this TQ of T structure, just like every other Floer homology. So if I give you any characteristic vector K on W, then I obtain a cobordism map that's associated to W and also this characteristic vector K. And this is a map from the Heegaard-Floer homology, let's say the minus version of Heegaard-Floer homology, HF minus of S3 to HF minus of Y. Now, the Heegaard-Floer homology HF minus of S3 is just some copy of F adjoin U, okay, which I think of as this infinite downwards tower. So what that means is for each characteristic vector on my cobordism W, I get a map from an infinite a copy of F adjoin U into the thing that perhaps I care about computing, HF minus of Y. Okay. So what I think of doing is what I do is I just take the set of all characteristic vectors on W. Okay. And for each characteristic vector on W, I formally introduce a copy of F adjoin U. Okay. And I shift all of these copies of F adjoin U just formally, such that the cobordism map. So it turns out that this, it's not very hard to see that this cobordism map is actually an injection from each F adjoin U tower into HF minus Y. You can tell this just for structural reasons. About negative definite cobordisms. But basically what you should think is there are all of these infinite F adjoin U towers, and each of them is embedded inside of HF minus of Y via the cobordism map on HF minus, okay? I shift the heights of these towers in such a way such that each embedding is grading preserving, okay? So for example, here I have drawn schematically three different characters, so this thing on the right, this Heegaard-Floer homology on the right that I've drawn is actually HF minus of sigma 237. This is just a schematic example. So you can imagine that I have three characteristic vectors on some particular standard negative definite plumbing for sigma 237. And the point is that each of these is embedded via the cobordism map for the different characteristic vectors on sigma 237, this plumbing, in some way. Okay, so for example, maybe this this tower on the left, which corresponds, which formally corresponds to some particular characteristic vector K0, is embedded by the cobordism map as I've drawn here. This infinite tower is embedded as this infinite, this red infinite chain on the right. Maybe this tower corresponding to K1 is embedded as indicated in this picture, and this tower corresponding to K2 is embedded as this other, this other infinite chain of reds on the right. Okay, and the point now you observe that, well, actually the images of these towers overlap. Okay, and the point is that actually you knew that they had to overlap. Okay, there's this relation called the adjunction relation, which tells me that if I, roughly speaking, if I have two characteristic vectors on this plumbing, and they differ by twice the Poincare dual of some exceptional sphere in the plumbing, then actually you know that the images of the cobordism maps have to overlap. Okay, that is to say they differ by some multiplication by U. I've written the sort of precise statement here, but the precise statement doesn't matter. Okay, what does that mean? Okay, what that means is that I could, the map from the disjoint union of these towers into HF minus of Y descends to the quotient of these towers. So what I could do is I could say, look, I know that the images of these towers have to overlap in HF minus of y. So in the domain, I'm just going to quotient out by the relations that I obtain that I know have to exist because of the adjunction relations. Okay, and then I get a map from some domain, which is obtained by taking an infinite number of f adjoint u towers and quotienting by some adjunction relation. I get a map out of this object into HF minus of y. Okay, so I get a map between f adjoint u modules. It turns out that the magic is that in certain cases, this map is an isomorphism. Okay, so that is the construction of lattice homology. So lattice homology is a thing that is constructed on the left. It is gotten by taking the formal f adjoint u span of all characteristic vectors on my cobordism and quotienting out by what are called the adjunction relations. Okay. Now, maybe I'm running a little bit late, so I'll gloss over some things. The proof that this construction, this is an isomorphism, this is called the lattice isomorphism theorem. The proof that this holds relies only on formal properties of Seiberg-Witten-Floer homology and its associated cobordism maps. So the very rough idea of the proof is that you induct on the size of your graph. So what you could imagine is that somehow, if I could have three different Plumbings, three different Plumbing graphs. I've sort of drawn these here down in the bottom here. You can imagine that I have three different Plumbing graphs, and the lattice homology objects I write down for the different Plumbing graphs fit into some combinatorially defined exact sequence. Okay. And then you essentially prove that, well, because Seiberg-Witten-Floer homology also fits into some sort of surgery sequence, you proceed via some induction on the complexity of the graph. Okay, and that's how you prove that in general, or for some class of negative definite Plumbings, your lattice homology is isomorphic to Seiberg-Witten-Floer homology. Okay, so that's a very rough idea of the proof. But the point is that if you have the same formal properties in whatever Floer homology theory you're considering, the lattice homology will once again be isomorphic to your Floer homology. Okay, and in particular, so recently my co-authors established a surgery sequence for Seiberg-Witten-Floer. Well, homotopy, but in particular, you could ask, does Seiberg-Witten-Floer homology satisfy the same surgery sequence as Seiberg-Floer homology or monopole Floer homology? And the answer is yes. And what that means is, as long as Seiberg-Witten-Floer homology satisfies sufficiently many same formal properties as Seiberg-Floer homology, the same argument will apply to show that lattice homology is isomorphic to Seiberg-Witten-Floer homology. Okay, now you actually knew that lattice homology is isomorphic to Seiberg-Witten-Floer homology because lattice homology is isomorphic to Seiberg-Floer homology, and Seiberg-Floer homology is isomorphic to Seiberg-Witten-Floer homology. But what I care about is that this procedure of looking at the cobordism maps, quotienting out the domain by this adjunction relation and looking at the induced map from these cobordism maps, what I care about is that map is what I am going to care about is that map is an isomorphism. Okay, so you know that map is an isomorphism for Seiberg-Witten-Floer homology. Okay, that's the point that I'm trying to get across. Now again, Seiberg-Witten-Floer homology is not the thing that we want to compute. We want to compute the Seiberg-Witten-Floer homotopy type. Okay, so even though this is long delayed, we're coming to this now. Okay, but let me once again sort of just stress what's happened here. Okay, so lattice homology is something that computes the Floer homology, however way you want to mean that Seiberg-Floer monopole or Seiberg-Witten-Floer homology of Y. It does more than compute the Floer homology of Y. It actually gives a particular presentation of the Floer homology of Y as an f adjoint U module. Right? It gives a presentation of the Floer homology as generated by all of these. There's one generator for each spin C structure of my cobordism, and then there are relations that correspond to the adjunction relations. Okay, and this is very important. It gives a preferred presentation of the Floer homology. Okay, another, I apologize for continually giving minor points, but another minor point that you, if you're paying very close attention to the example that I gave, it turns out, in the case of sigma 237, I only had to use 3 characteristic vectors to present the Floer homology of sigma 237. Whereas in the discussion before, I said you have to take every characteristic vector on your cobordism. There is, of course, some sort of theorem that tells you you don't have to consider every single characteristic vector on your cobordism. You can get away with a finite set of characteristic vectors. And in fact, the finite set of characteristic vectors can be arranged such that they occur in a path, in the sense that it's actually a finite sequence of characteristic vectors, and each element of the sequence differs from the previous element by twice the Poincare dual of some two-sphere, exceptional two-sphere E in your plumbing. Okay, so that's a structural theorem about lattice homology. Okay, all right. Are there any questions? No questions. Okay. All right. Let me finally get to the point. 40 minutes into the talk. All right. So how do we construct this lattice homotopy object? Okay. Let me do an example. And actually, once I do the example is sort of laughably easy. And once I do it, the general algorithm will be clear. Okay. So let me cast your mind back to the example of sigma 237. Okay. So here I've drawn both the Floer homology of sigma 237. And what I showed you is the Floer homotopy type of sigma 237 on the left and the right, respectively. And let me remind you that the thing on the left is the Floer homology of sigma 237. But once again, I stress to you that somehow you should think of the Floer homology of sigma 237 as having this preferred presentation coming from lattice homology, which is 3 copies of f adjoint u glued together as indicated on the left. So there are these 3 towers, and the middle tower is glued to either tower, to the tower on either side of it, after a multiplication by u of the towers on the left and the right. Okay, that's what these horizontal arrows indicate. They just mean you glue these towers together. And this obviously gives you the f adjoint u module on the far left. Okay. And on the right-hand side, I've drawn for you what I have said as the Floer spectrum of sigma 237. And I wish to point out to you something seemingly very stupid, which is that, again, the Floer spectrum of sigma 237 also has, in some sense, a presentation of 3 things glued together. It's 2 copies of S2, which are glued along a common copy of S0. Okay. There's some formal similarity between the thing on the left and the thing on the right. You might think this is a very stupid observation, but it's not. Okay. And the first reason it's not is, let me convince you that if I calculate the equivariant homology of the thing on the right, I get the thing on the left. Okay. It's a very pleasing computation. Now, what do I mean by the equivariant homology? In this case, I mean the co-Borel, S1 co-Borel homology. If you remember, the S1 co-Borel homology is the thing that I told you corresponds to HF minus. Okay. Now, I actually haven't defined the co-Borel homology for you. I defined the Borel homology. So you might be wondering how I'm going to compute the co-Borel homology on the right. Well, this is why it's so pleasing. It essentially does not require the definition of the co-Borel homology. So the only thing that I'm going to require you to really believe is that the co-Borel homology of a sphere Sn is, in fact, a single f adjoint u tower shifted in grading. Okay. Why is that believable? Well, it's because I told you that the Seiberg-Witten-Floer spectrum of S3 is S0. So the co-Borel homology of S0 should be the same as HF minus of S3, which is, of course, just a copy of f adjoint u. Borel and co-Borel homology, just like regular homology, satisfies invariance under suspension. The only thing that happens when you suspend is you get a grading shift. So if I take Sn, which is a suspension of S0, then I should again get an f adjoint u tower, except shifted in grading. Okay. So what that means is that if I take the co-Borel homology of each of these 3 pieces on the right, S2, S0, and S2, I once again get 3 copies of f adjoin u, except that the 2 copies of f adjoin u corresponding to the S2s are shifted in grading relative to the copy of f adjoin u corresponding to S0. And of course, when I glue these 3 things together, what will happen but that essentially I identify these towers, these f adjoin u towers, as subtowers of the other. So it's not very hard to see that if I have an inclusion of one sphere into the other, then on the level of co-Borel homology, what could happen? But that induces the inclusion of one tower as a subtower of the other. And so it's very easy to see that if I take, because co-Borel homology is going to satisfy some sort of Mayer-Vietoris principle. If I take the co-Borel homology of the thing on the right, then I will, in fact, not just get the f adjoin u module on the left. Indeed, I will get what I claim to you is HF minus of sigma 237. I will get HF minus of sigma 237 with the presentation that came from lattice homology. Okay. Now, why is that good? Okay. So that immediately gives you some sort of conjectured construction for the Seiberg-Witten-Floer. If you like this picture, then you might say, I immediately obtain a conjectured picture for the Seiberg-Witten-Floer homotopy type of any of these, let's say, Seifert-Fibrid homology spheres. What is the conjectured construction? I just take the output of lattice homology, as in the left-hand side of this picture. I remember that the output is giving me a presentation for the Heegaard-Floer homology, which is the same as the Seiberg-Witten-Floer homology, as these infinite copies of f adjoin u towers glued together along subtowers. And I just write down some sequence of spheres, which are glued along subspheres, such that taking the co-Borel homology exactly recovers this presentation of the f adjoin u module. Okay. And that's the lattice homotopy type construction. Okay, so and it's 100% combinatorial because the output of lattice homology is 100% combinatorial. I mean, so you just take this graded root output, which secretly is this presentation of this f adjoin u module, and with an eye on the previous example, you just write down exactly the space whose co-Borel homology recovers this presentation. Okay. Now, okay, so you might say, oh, this is very good. This is very impressive. So this space certainly has the right co-Borel homology. You might be very happy. Unfortunately, this is not very impressive, right? The whole point of homotopy theory is that the homotopy, there are many spaces with the same homology, right? I mean, that's the whole point. The homotopy type of the space is supposed to be stronger than the homology. So just because the space has the right co-Borel homology doesn't mean anything. Okay. However, what is actually much more impressive is that the space that you construct in this manner admits a map, an S1 equivariant map into you can prove that it actually admits a map into the actual Seiberg-Witten-Floer spectrum of Y. Okay. And why can I map the combinatorial space that I've just constructed for you into SWF of Y? Okay. Well, it's just an upgrade of the lattice homology isomorphism idea that I told you previously, right? So Seiberg-Witten-Floer spectra, just like any Floer homology, again, satisfies the fact that, I have cobordism maps. So for each spin C structure on my cobordism, I get an S1 equivariant map from the Seiberg-Witten-Floer spectrum of S3 into the Seiberg-Witten-Floer spectrum of Y. Now, remember, I told you the Seiberg-Witten-Floer spectrum of S3 is a copy of S0, okay? And while that statement that I just told you is not quite correct, right? In the setting of Floer homology, your cobordism map comes with a particular grading shift, okay? In the setting of Floer homotopy, the analog is that the quote-unquote cobordism map is not actually a map from SWF of domain into SWF of codomain, but it's a map from a suspension of SWF of domain into SWF of codomain, okay? But what is a suspension of S0 but some other S1 sphere, okay? So what that means is that in this context, for each characteristic vector of my cobordism, I get a map, an S1 equivariant map of a sphere of some dimension into SWF of Y. Okay, just like in the case of Floer homology, for each characteristic vector, I got a map from some shifted F adjoint U tower into the Heegard-Floer homology or monopole Floer homology of the target. Okay, and then what you can prove, so of course that means that I get a map from the disjoint union of all spheres, indexed by characteristic vectors of my cobordism into SWF of Y. And what you prove is you prove a similar thing in the homotopy type setting as you had in the Floer homology setting, which is some sort of a junction relation, which is that if I have two successive characteristic, two characteristic vectors of my cobordism, then the Floer homotopy maps from the spheres corresponding to those characteristic vectors are not totally independent from each other, okay? And in fact, essentially, if I have two characteristic vectors, one differing from another by twice the Poincare dual of some two-sphere, up to homotopy sort of have an inclusion of one sphere into the other, and then up to homotopy, the Floer homotopy map of the bigger sphere covers the map on the smaller sphere, okay? And so what that means is that you get a map from the quotient of these spheres into SWF of Y, just like I had in the case of Floer homology. And that's what defines this map from this combinatorially constructed lattice homotopy object into the actual SWF of Y that I care about. Okay, so what does this mean? This means that I've produced for you a space, an S1 space, which has the right co-Borel homology. So the co-Borel homology in my space is actually the Seiberg-Witten-Floer homology of Y. And my space admits an actual map into SWF of Y. And if you think about it, that map actually induces the isomorphism on co-Borel homology, okay? Because what will happen when I take the co-Borel homology of my combinatorial lattice homotopy type? Well, I will recover the presentation. I will not just recover the correct co-Borel homology, but I recover the Floer homology of Y with the lattice homology presentation, okay? And I know that the lattice homology is isomorphic to the Seiberg-Witten-Floer homology, the lattice map that I told you about before, which is constructed by looking at the maps on the homological level, is an isomorphism, okay? So the point is that you now have a map between the two spaces, which induces the isomorphism on the homological level, okay? And it turns out that that is very strong, okay? I mean, in the non-equivariant case, we're probably all familiar, with the fact that, let's say if you have a map between simply connected spaces, the Whitehead theorem or whatever, it tells you that, a weak homotopy equivalence is good as a homotopy equivalence, right? So what you can show is that in this setting, having an S1 map between the two spaces, which induces an isomorphism on co-Borel homology, actually suffices to show that, your two maps are S1 homotopy, your two spaces are S1 homotopy equivalent. Okay, so that's how we prove that these spaces give the correct construction, give the correct homotopy type. Okay, all right. So that's an overview of the construction and how we prove this is the correct Seiberg-Witten-Floer homotopy type. For experts, you probably know that one of the really interesting things about Seiberg-Witten-Floer homotopy type is that it's not just an S1 theory; it's a pin-2 equivariant theory. So you can put a pin-2 equivariant, pin-2 action on SWF of Y. It turns out that you can also put a pin-2 action on this lattice homotopy. And in fact, you can show that the pin-2 homotopy, this pin-2 action on the lattice homotopy computes the pin-2 equivariant homotopy type of Y. The proof of this is rather more complicated. I've glossed over it, and it's requires a lot more work. The reason is that in the discussion that I've told you, it turns out that the map from the lattice homotopy type into the actual Seiberg-Witten-Floer homotopy type of Y is not evidently pin-2 equivariant. The reason this is roughly speaking, it is pin-2 equivariant if the plumbing in question is spin. for people who know a little bit about lattice, have thought about this a little bit. It's pinto-covariant of the Pluming spin. It's not necessarily pinto-covariant if Plum is not spin. You have to do some hard homotopy theory to prove that in the latter case, the map can be sort of isotoped to be pinto-equivariant. So I'm gonna gloss over this, but we do have the result also in the pinto category. It requires a significant amount of work on top of the idea that I've told you about. Okay. All right. There were more things to say, but I think I've run a little bit late, and it's close to the end of the talk anyway. So maybe I can end it here. Are there questions?
Typically go an hour, so you're not late. You're even being generous to the question.
Okay, let me say it then. I can say like a few other things. Okay, so well, okay, let me think how to best compress the thing that I wanted to say. Okay, fine. In that case, maybe if I am allowed to go a few minutes over. So let me say a few more things which I think are really interesting. This part of the talk is much more speculative. Okay, so I've constructed for you this lattice homotopy type. I think a really interesting question is, where does it come from? I mean, is it just some combinatorial sleight of hand? I wrote it down and I proved to you that it was the right one. I think there are some interesting indications that there's some sort of deeper analytic or geometric meaning for the construction, and that's what I want to talk about here. Okay, so let me sort of very quickly go over, gloss over some slides. So I'm gonna skip this. Okay. So let me get to the points. Okay. There's a very slightly different reinterpretation of the construction that I've given you, which is the following. Okay. So previously I gave you the example of sigma 237, which I told you take two copies of S2, you glue them together along the north and the south pole. Okay. That gives you this picture that I gave before. I could very trivially tell you a different construction, which is inside of H, the quaternions, I have two copies of C, right? I have C and I have J times C, and these are two copies of C, which of course intersect at the origin. Okay, and I take these two intersecting planes inside of H and I compactify at infinity. Okay, and of course, once again, I would just get two spheres glued together. Okay, but my point is that instead of taking all of these spheres and gluing these spheres along subspheres, what I could view the construction of the lattice homotopy type I just told you as I have some very high dimensional, let's just say complex vector space, and I have a bunch of hyperplanes, not hyperplane, but subspaces of this subspace, this complex vector space, which intersects along subspaces of a particular dimension of varying dimensions, and I compactify at infinity. And you can see that this is just trivially a rephrasing of the way of taking a bunch of spheres and gluing them together along a bunch of S1 spheres and gluing them together along subspheres. Okay, so you can view actually the construction as just some sort of arrangement of subspaces inside of some Cn. Okay, and then you could say, well, what do those subspaces have? Does this have any meaning? Right? Is this just really just totally combinatorial? I wrote down the dimensions of those subspaces, of course, correspond to the dimensions of the spheres, which correspond to the heights of these leaves inside this graded root, inside this tree. And you could ask yourself, okay, I mean, like, is it really just I looked at the tree and I wrote down these numbers, and these are the numbers that are the dimensions of the spheres, aka the dimension of these subspaces, or did the subspaces have some meaning? Right? Do the fact that I have some sort of collection of vector spaces of particular dimensions that intersect along subspaces of particular dimensions, does this have any meaning? And it turns out, so this is the example that that is to say, do these vector spaces and the fact that they're subspace of each other arise naturally in terms of the topology or geometry of any of the objects under consideration, in particular, this plumbing W? And it turns out the answer is yes. Okay. And the really interesting thing, I think this is sort of speculative, and apologies for going a little over time. I'll finish in a few minutes. But it turns out that this is very related to work of Andras Nemeti in understanding singularities in algebraic geometry. What is the 10-second overview of this? Well, if you actually look at so what are the dimensions? What are the dimensions of these spheres, right? I told you these are the heights of these towers. The heights of these towers correspond to the grading shift of the maps in Heegaard-Floer homology, which are associated to various spin C structures on the cobordism. Well, it's an underappreciated fact that actually the grading shift in Heegaard-Floer homology is up to a constant shift equal to the Riemann-Roch function. Okay, what do I mean by this? So in this context, what happens is that if I take this plumbing and I look, so each characteristic vector on my plumbing corresponds to a particular, I can make it correspond to a particular divisor via correspondence with the canonical class of my plumbing. The plumbing has a preferred complex structure. It corresponds to a particular divisor and a particular sheaf of holomorphic functions on this plumbing. Okay. And it turns out that the number that comes out of the grading shift actually is the difference in dimensions of, it's the holomorphic Euler characteristic of this, the sheaf of holomorphic functions. Okay. What does that mean? What have I just told you? It means that each of those dimensions, each of those numbers that appear in this construction of the lattice homotopy type is actually already the dimension of a complex vector space, or almost the dimension of a complex vector space. It's the dimension of the formal difference of complex vector spaces, this being H0 minus H1 of some strange sheaf of holomorphic functions that corresponds to this characteristic vector in some way. And so, unfortunately, now I really am running over time, but so it turns out that you can interpret the construction, this lattice homotopy type construction, in certain favorable circumstances. I'm really sort of sweeping a lot of things under the rug. In certain favorable circumstances, because, for example, you could imagine that as I vary the characteristic vector, I vary the sheaf of homomorphic functions that's being considered. There are natural maps, between H0 and H1 associated to different sheaves. Okay, so these numbers that come out, they are dimensions of vector spaces, or at least dimensions of formal differences of vector spaces, and these vector spaces have maps between each other as I vary the characteristic vector / divisor in question. So the construction of the lattice homotopy type can actually be interpreted in terms of this algebraic geometry or study of these holomorphic Euler characteristics of this complex structure on this plumbing. All right, so I think I will end it there. Are there other questions?